As I mentioned at the end of the last video, when you're solving the types of problems that we've seen quite commonly now, where you have sliding components or you have rotating components, just keep doing what you're doing. You're deriving kinematic equations and you're already incorporating those constraints. This week, we're just introducing another type of problem, so where the components just have a slightly different type of movement. And the goal is to learn or to practice how to incorporate the kinematic constraints that are typically associated with those types of problems. So what types of problems are those? Well, if you think back to your statics class, one of the perhaps more common elements in the systems that you analyzed was a pulley, right? Perhaps you had an example that looks something like this, where you had two masses. You had mass 1 and you had maybe mass 2 here, and then you have a string connecting them over this pulley here, and that string length is equal to L, and L is constant, meaning it doesn't change length. So L is constant. Right? And so here you can imagine that if I were, I'm going to do some simplification here. I'm not going to necessarily take into account the fact that this is rounded. We'll just imagine that this radius is really, really small of this pulley here. But if this is y1 and this distance is y2, and this point here is on mass 1 is 0.1 and this is 0.2, so that if I change y1, I'm going to change y2, right? So if I were to pull on this thing, as y1 grows, y2 is going to decrease. So you could write that as a kinematic constraint, oops, where you have y1 plus y2 is equal to L. And so again, you could also write that out as y1 plus y2 minus L equals 0. So that's the holonomic constraint equation. And so the purpose of the problems that we're going to do this week is to get you back into the groove of using these pulley systems, right? If you use them in statics, you can be sure that we're going to go over examples with them in dynamics where now you actually pull on one of these masses and something's going to move, right? So we just want to make sure that as you're doing these types of problems that you're properly considering what those constraint equations are and making sure that they exist in your kinematic equations. And so that's really the big point of this this week's material. So with that said, let's actually walk through an example problem. So here we'll have our cart and pulley example. So I have a cart, and that cart can move along the horizontal axis. That cart also has a pulley at its center, and you have a string that's fixed here, and that string goes around the pulley and then hangs down here, and then attached to the other end of the string is a mass, and this point on this mass is P1. So some things that I know, well, first of all, let me just draw my, I'm going to draw my fixed reference frame. I have A1, A2. So I want this P1, I'm going to call this point here where the pulley is, that's P1, I'm going to call that P2. Know that this distance here from the origin O to P2, that's going to be X. This here is going to be Y. And then I also know this height here. So just looking at this system, you can start to write down what the position vectors are of RP1 and OP2. So for instance, I can write that ROP1, so this point here, is going to equal XA1 and then minus YA2. I can also write that ROP2 is equal to just simply XA1. And so let's just focus on this equation here, right? So this one has only one variable, x, right? So again, this cart can only translate or move in the horizontal A1 direction. ROP1 has two coordinates at the moment, right? So it has x and y. However, if you look at this system, it actually only has 1 degree of freedom, right? So if I move this point P2, that will change. So if I change this x, it's going to change y, and that's because x and y are related through this string, which has, which has a length L. And so we need to incorporate this kinematic constraint imposed by this string here in order to properly write this position vector in terms of only one coordinate, right? One coordinate because it only has 1 degree of freedom. Okay, so let's start by defining our constraint equation. We have this length of our string. We know that that length is equal to L. We know that this component here has a length of y. And now we need to get the length of this component. Well, we can use Pythagorean theorem, and because we have x and we have h, so we can write this out as the square root of h squared plus x squared. And I'm just going to write that out as y plus h squared plus x squared. We'll put this to the 1/2. And so this is our constraint equation. And we can rearrange this equation, and we can write it in terms of y. So we can write now that y is equal to L minus h squared plus x squared square root. And now we can write this vector, ROP1, we can take into account that x and y can't change independently by plugging in this expression here into this here. So we can write our OP1 is equal now to XA1 minus, here we have L minus h squared plus x squared square root XA1 minus L plus this. Okay, oh, A2. Right, so now we have correctly taken into account the fact that we had this kinematic constraint by incorporating it, rearranging it such that we wrote it in terms of y as shown here. We can use that value of y, plug that back into our position vector, and now we can write this whole position vector in terms of x. Right, so again, now our position vector here makes sense because it matches the fact that we have a 1 degree of freedom system, and here we now only have one coordinate, right? The L and H, those are constants. And now going through and taking the derivatives, of course, you can get now the velocity and the acceleration. All of those will be in terms of x and its derivatives. It gets a little messy, so I'm going to leave that just for the notes for you to look at and to calculate on your own. But this is how, when you incorporate a kinematic constraint into your kinematic equations. Start with incorporating it into that position vector, because again, we're only working with holonomic constraints. So you can take that constraint and you can implement it into that position vector. And then once you have that set, once you do the derivations or take the derivatives and get your velocity and acceleration terms, everything will be taken care of. So this is it. This is really the main point of this week, and your homework problems, at least the first few homework problems, is to make sure that you know how to incorporate this constraint equation into your position vector for systems where you're not already intuitively doing that.